first of all, thank you to the organizers for organizing this very interesting symposium. And today, the last talk, I guess, for today and for the symposium will be about Axion-Like particles, and in particular, where my slides are switching, where and how to search for them. I will be talking about specifically using the Fermi Large low energy technique in attempt to search for these particles. So we've heard quite a bit about Axion-Like particles. This is just kind of a quick reminder as to what they are. They come as an extension of the idea that was introduced in particle physics to solve the charge parity problem, the idea of axion field. And these particles are weakly interacting sub-eV particles, meaning that they're low mass particles reaching the ranges of about 10 to the minus 10th and lower EV. Even though they're very light, these particles are do satisfy cold matter requirements. They have feasible interactions with the standard model particles, as well as being cosmologically stable. There are two main ways in which these particles are hypothesized to be produced. The first one is shown in the upper right corner of my slide. It's the misalignment mechanism. And this mechanism is akin to the inflationary model of the universe, where you have some kind of a potential well being filled up with a dynamical field that oscillates with a given density. And this density is shown here. And we see that for a range of masses of the Axion-Like particle, these densities can actually describe what we observe in the universe as dark matter. The second way of producing these particles, and the one relevant to my research, is the Primakov process. And the Primakov process relies upon the assumption, I don't know why my slides are switching, relies upon the assumption that the Axion-Like particles, when entering the magnetic field, will be converted into gamma rays with this coupling constant. Okay, and we've heard quite a bit of research being done with Fermi in context of dark matter searches. So just a quick reminder as to about the Fermi Observatory. We have two instruments on board for Fermi. We have GBM, or gamma ray burst monitor. And as the name suggests, its primary purpose is to observe gamma ray bursts. I will emphasize one thing from this list of characteristics, and that is that the energy coverage for GBM is about 8 keV to 40 MeV. The second instrument is in this orange box. It's LAT, or Large Area Telescope. It's a pair production telescope, and also emphasizing that its energy coverage is from about 20 MeV to more than 300 GeV. Okay. So what can Fermi do in terms of Axion-Like particles? So hypothetically, these particles can be produced in high energy environments, such as a core collapse supernova. And the idea here is that in a collapse of a massive star, there will be an abundant amount of thermal photons produced. In the local magnetic field of the core collapse supernova, they will undergo the inverse Primakov process, where they will be converted into Axion-Like particles and will travel undisturbed until they reach the magnetic field of the Milky Way, where they will undergo the conversion into gamma rays via Primakov process. So the idea is that gamma ray observatories such as Fermi could potentially be used to search for these particles. Here I show the temporal and energy evolution of the gamma ray emission that we should expect from the ALP emission. And on the left side, I do so for the 10 solar mass progenitor, and on the right side, it's the 18 solar mass progenitor. And this theoretical model suggests that the duration of the ALP burst should be of the order of 10 to 20 seconds or so. And of course, we can extract the spectral shape that we should expect from ALP emission. And here I show two spectra for two different progenitor masses. And one thing that is worth noting is the fact that the peak energy of this spectral shape is at around 70 MeV. This is a very unique spectral signature, and we don't expect any other physical processes on these time scales to have this kind of a spectral signature. So actually seeing this in the spectra of some high energy sources would be a smoking gun signature for ALPs. Now I want to combine the two slides that I already covered. I said that the energy peak for the ALP spectral emission is around 70 MeV. And then I talked about the energy coverage for GBM and LAT on Fermi. And both of these instruments seem to have most of the ALP photons, ALP counts in their energy ends. So this can be a challenging problem because the sensitivity at these energy ends reduces for Fermi for both instruments. One way to account or address that issue is actually using this so-called LAT low energy technique, which was developed a decade ago by LAT team in order to search for transients going down to 20 MeV. The goal of this method was actually to maximize the effective area of the LAT instrument for the low energy regime, and it is done by relaxing requirements on the background rejection. Now, this comes at a cost. We do get more signal, but we also get more background. And there are some systematics associated with it. I won't go in detail about it, but the LAT team has actually done a pretty nice job in terms of addressing those when doing the analysis. Okay, another thing that when we want to search for these particles, I've talked about magnetic fields. We need to make some assumptions about magnetic fields. In the research that I'm doing, so far we've only been considering the Milky Way magnetic field simply because any other magnetic field is too complicated or we have too little information about. And we are neglecting the intergalactic magnetic fields. Any additional conversion that of ALPs into photons that happens in the intergalactic magnetic field would only result in a higher count number. So any results that we actually report are conservative as we do receive less counts because we neglect this intergalactic magnetic field. On the right side here, I showed the conversion probability map for the Milky Way magnetic field using the Jensen and Farrar magnetic field models. And we see that the conversion probability between ALPs and photons ranges from maybe 10 to the -6 to 0.1 or so. Okay, so the first question that I wanted to answer here is how far can Fermi actually see using this LLE technique? To do that, what we did was we took a number of backgrounds from the GRB observations in LLE, and we considered those ranges of backgrounds and injected some ALP signal on top of those with different normalizations. The nice thing about scaling the ALP spectrum is that it follows the usual inverse distance square law, in that once we know the normalization for which we can detect the ALP signal, we can also deduce the distance. So what we do is we produced a number of simulations for these spectra and finally on top of the background, and finally we did a model comparison analysis in which we compared fitting the ALP signal and fitting the background only signal, and found for which values of normalizations actually adding the ALP spectral component would improve the fit. From there, we deduced the distances to which Fermi LLE would be sensitive to. And that is what this plot shows. The various diagonal lines are the distance limits for different background levels. And the dashed lines are actually what Fermi LLE would be sensitive to, depending on the coupling. Also, I here in this table, for convenience, I also kind of just list different distance limits for various conversion probabilities. And all of this I want to mention is actually already summarized in the paper that we published a few months ago. There's one thing that I did want to mention, and if you look at this table, you will see that the distance limits seem to, of course, depend on the background levels, but not in the way that you would expect. So actually, for the lowest background levels, we see that the distances to which Fermi LLE can reach are actually the lowest, as compared to the higher background levels where we seem to be able to reach further out. This is an entirely instrumental, there's an entirely instrumental explanation for this. And I show that here. Here I show the background fluence as a function of incidence angle. Incidence angle is the angle at which photons fall onto the detector plane. And we see that for lower incidence levels, we have higher background levels. And then this plot here actually shows the effective area of Fermi-Lat LLE for different background levels. And that is related to the, as I mentioned, incidence levels. So for high backgrounds, we get higher effective area, meaning higher background levels and also higher signal levels. So this is where the justification comes in. Also, very briefly, we also considered GRB detections in Fermi LLE. The reason why we're looking at GRBs is because long GRBs are associated with core collapse supernovae. And here we look at a number of LLE detected GRBs with the selection criteria. I won't go into detail about that, but we don't find any significant detection of ALPs within those GRBs. One of them has a log likelihood ratio of 5.8, which already is not significant. It's about 2.4 sigma or so. But when including the trials factor, that significance goes completely out of the picture. And finally, I kind of want to, I'm going to leave the summary up. I won't go through it because of the time, but if you have any questions, please let me know and I'll try to answer them.